So now we have a second talk by Sigol Thomas from George Mason University. Her title is Dynamics of Auto-Automorphisms of Action on Automorphism Group Action on Finite Field Points of Character Varieties.
Hello all. Thank you for joining the session. So yesterday I talked about introduction to character varieties, where I mainly defined what character varieties are and talked about some of the generators of the invariant ring. So today I'll be talking about the action of outer automorphism group on the character varieties, but I'm looking at the finite field points of these character varieties. Okay, so the outline of the talk is that first I'll briefly recall the definition of character variety, and then we look at the action of the outer automorphism group on these character varieties. And then I want to understand the dynamics of this action, right? So the way there are different approaches to understanding the dynamics. So the way I do this is I start with the transitivity, looking at the if whether the action is transitive or not, and then from there try to find a what is a good candidate for a large orbit. So kind of want to see what is this action, how much of a mixing is this action doing on the variety. So trying to kind of find a large orbit. And then we define something called asymptotic transitivity. It is to trying to imitate or finding an analogy similar to ergodic action when you have a set with a measure. So that's the outline of the talk. Okay, so definition of character variety. So a character variety has two components, and one is a group, and which is I'm working with a reductive complex affine algebraic group. And algebraic group is a group with a variety structure, with a variety structure in it, such that the morphisms of the variety are also, such that the group operations, inversion, and the multiplication are also morphisms of the variety. And gamma is a finitely presented group. And basically what we want is basically the character variety is so we want to look at the representations of the homomorphisms from gamma to G, these homomorphisms, and we look at the conjugation orbits of them. And so we are looking at the homomorphisms up to conjugation, but not just the regular conjugation orbit, but we are looking at, we are considering two orbits, two homomorphisms equivalent if they're closure in the Zariski topology intersect. So if their Zariski closure intersect with each other, we consider them the same. So this is the equivalence relation, and these conjugation orbits are the G character variety of gamma. So this is the definition we will be working with, and most of the time what I will do is I'll start working in the space of homomorphisms, and then we look at, okay, up to conjugation, try to extend that to the conjugation. So up to conjugation, how can we extend that? And then look at, okay, which orbits will be closed, and then consider those points. So that's the idea. Okay, so what is the action? So so let me first define what is the action that I want to study. Okay, so I'm looking at, suppose gamma is a finitely generated group, which has R generators, gamma 1 to gamma R, and G is a reductive affine algebraic group over integers. And I mentioned yesterday, I want integers because I'm looking at the finite field points of the variety. So I want the variety to be defined, or the polynomial, for example, the polynomials that define the variety to be defined over integers, so that it makes sense to look at the finite field points. And outer automorphism group is just to recall the definition, is just the quotient of the automorphisms of gamma mod out by the inner automorphisms, which are basically the automorphisms defined by conjugation. And it makes sense because we are looking at conjugation orbits, so inner automorphisms are just going to be trivial on the character variety anyway. So the action, the way we define this action is, so out gamma acts on hom gamma G in this way. So if alpha is an element of is an outer automorphism and rho is a homomorphism, then we compose alpha inverse. So we apply alpha inverse to the generators, and then we compose it with rho, and this is the action, and this is this is a well-defined action, and this is the action on the Hom set, and then it extends to a co-action on the coordinate ring, and then it extends to an action on the character variety. So basically the action is we take the inverse of any action of any automorphism is we take the inverse of this automorphism, and it acts precompose it with the rho. That's the idea. Okay. Now, why do I care about this specific group of outer automorphism group? What is special about this is, first of all, it acts naturally on character varieties. And if we look at gamma as a fundamental group of, suppose gamma is a fundamental group of the closed oriented surface of genus G greater than 1, then out gamma is the isomorphic to the mapping class group, and mapping class group is the group of isotopy classes of orientation preserving diffeomorphisms of the surface. So mapping class group action on the mapping class group action on the character varieties is historically relevant, and this action is, so this has been well studied, especially when you're looking at the varieties over the complex numbers. For example, when G is a compact Lie group, then the action is ergodic, and when gamma is a closed surface, is a fundamental group of the closed surface group of genus G greater than 2. So, but these were, like I said, this is in special cases. There are different other certain cases where this action is proved to be ergodic. But we want to look at the analog of this topological dynamic in an arithmetic setting. So we want to, when we are looking at when we look at these compact Lie groups, there is a natural measure, geometric measure defined in there. So it makes sense to look at the topological dynamics of those more, but in an arithmetic settings over finite field, it makes more sense to, we don't have a natural, there are some measures, but there are no natural invariant geometric measures, which helps us. So we define, after looking at transitivity, we try to kind of develop an analogous measure like ergodicity, and we call it asymptotic transitivity. I will get to that at a later point in the talk. First, what I'll do is I'll look at the transitivity property of this action. Okay. So first, the idea is, okay, so this is a theorem which tells us when this action is not transitive. Okay, so suppose gamma, if gamma is a group generated by gamma 1 to gamma r, and G is a reductive affine algebraic group over integers, and the idea is, if there is a homomorphism, okay, and before that, here f of rho, I mentioned earlier, just to refresh your memory, I mentioned that we can embed the set of homomorphisms into the R product of G by the evaluation map by just sending rho to rho of gamma 1 to gamma R. So this F is the evaluation map. So if there exists a rho such that the image of it, which is sending each of the generators to an element of a subgroup H of G, and also there is another element Y in the complement of this G, such that it is the image of some homomorphism in the Hom set. So if that is the case, then this action of out gamma on the Hom set is not transitive. So the idea is, if you can find so what this theorem is trying to say is, if we can find a So if G, this is G, and then suppose I can find a subgroup H, and if there is a homomorphism rho that is mapping inside completely into H, and there is another, say, mu, which is mapping to the complement of that, then the action cannot be transitive. Okay, so the general idea of the proof is that so if rho is a homomorphism, and then suppose the image of this rho under the evaluation map is these elements x1 to xr, which is, like I said, it's landing inside the R product of the subgroup. Okay, and then we look at and alpha is an element of out gamma, and so we look at alpha inverse of gamma I is some word wi, right? And in these generators, gamma I to gamma I. So just I'm just indexing it here by I sub 1 to I sub s, and with powers a sub I respectively. Okay, then when we apply this rho to this wi, the word wi, its rho is a homomorphism, so we can it's just rho of gamma I to the power a to the power I1 up to rho of gamma I sub s to the power a sub I sub s, which is each of this, like I mentioned, the image of rho is independently just the x sub i's, right? So this is alpha dot, this is the image of the action under alpha, which is landing in HR again. So this means we are never going out of the subgroup H. So basically what we are saying is, if we start out with a point here, then under this action, we never leave the subgroup there. So which means the orbit of this is always going to stay inside. Orbit of rho is always going to stay inside H to the power R, the R product of H. And if there is some other element which is in the complement of that, then it cannot be transitive, because there will be mutually there will be no intersection between those two orbits. So that's the general idea. And this is one of the results that we will keep using again in other cases as well. Okay, so let me show an example, like with very specific groups, how this action look like. So one of them, sorry, I meant to say R generators here. Okay, so suppose gamma is a abelian group generated by R elements, and G is SL2FQ. Okay, and then so the outer automorphism group of ZR is GLRC in general. It's a set of all R by R matrices, invertible. Sorry, I have given here determinant plus or minus 1. Yeah, so set of all invertible matrices with integer entries, and since it is integer, the determinant, and if it has to be invertible, it has to have determinant plus or minus 1. Okay, so I want to choose the simplest case, which is when R equal to 2. So we have out of Z2 here, which is GL2C, and our gamma is just the abelian group generated by X and Y, but they commute with each other. And our G is SL2FQ. And I want, so how does this action look in this case, right, specifically? Okay, so let's look at the action. So rho is a homomorphism from Z2, C cross C to SL2FQ. And suppose the image of the generators are A and B, capital A and capital B, which are elements in SL2FQ. And in this case, and then alpha is an element of GL2C. I'm going to choose alpha inverse to be ABCD, because that's the one that we will be that's the matrix we'll be multiplying with. And so alpha will be plus or minus D minus B minus C and A, just the inverse of that matrix inverse. And I already mentioned the determinant will be plus or minus 1. Okay, so we defined, I already mentioned earlier, the action is defined to be alpha dot rho is going to be rho of alpha inverse of xy, which is multiplication by this matrix GL to alpha inverse corresponding to alpha inverse here. And that gives us rho of ax plus by and cx plus dy. And rho is a homomorphism. So we end up with this. And since this is matrix multiplication, this row of the multiplication here reduces to being power. So we end up with a to the power a, b to the power b, because we took a rho of x to be capital A and rho of y to be b. So this is the action basically. So it's sending each element to this product of matrices, right? So what I did was, to get an idea of how this action looked like, I looked at the orbits of this action. So this is just to give a visual picture of how this orbits look like. This is the simplest case where the prime p is equal to just 2 elements. So we only have 0 and 1. And there are 6 orbits. This is just the identity matrix, which is the central element. It's by itself. And these are the other 3 orbits, other 4 orbits in SL2, F2. So you just by looking at it, we can see it's not transitive. In fact, SL2, so just to give an example, right, to show an illustration of what I mentioned in this theorem is that, so all we have to look at is basically, we look at this this group, right, and we look at the subgroups of this, right, and this is actually isomorphic to S3, the symmetric group in 3 elements, so which has proper subgroups, right, we know. And so we have a subgroup, and we have homomorphisms that land inside each of those subgroups. So therefore, this action is not transitive. So this is a very simple illustration, most simplest case that we can do with this case. And then I looked at just the next case, which is when p equal to 3. And that's also not transitive. And I want to say one more thing, that this is not GL2C is this is not all the elements, right? Because I just looked at the action of the generators. But since this group is simple enough, I can conclude that there is no way you can get from this orbit this by using any element of GL2C. Okay, but that's not. Yeah, sorry. There's a question.
It's not G2. I thought it was G2. And why are you looking at GL2? Sorry about that, but is it not?
Oh, sorry. Yes, sorry. I'm sorry. Yeah, you're right. My bad. I was a typo. I meant to write Z2. This was the question.
Yeah. And then what about?
Yeah.
That's the monodromy group. Automorphism of
G2. Sorry, which one? This one, GL2C.
That's the.
That's the outer. That's the outer automorphism group of Z2. Out Z2.
That's auto. I thought it was SL2. I mean, maybe I'm. Anyway.
Oh, so I'll go once more. So I'm looking at the action of. Okay, let me show. Yeah. So see, I'm looking at the action of out on the home set, right? Out of gamma, and my gamma is C2. Yeah. So it is DL2C. Yeah. Yeah, no problem. Yeah. Okay. So so I wanted to say, so this is using Mathematica, and to get this, I just generated the action using the generators of GL2C. So it's not always enough to conclude, because I'm just looking at the generators. There might be other elements in GL2C which can take one orbit to the other, but in this case, this is conclusive. These are all the orbits under the action of GL2C, which is not completely true in the. So I should say orbits by generators. So I was looking at 3 specific generators of GL2C. So under those action, these are the orbits of this home set in from homomorphisms from C3 to SL2F3. Okay, this is just to get a feel of how the orbits look like. Okay. Okay, so now that we know that the action is not transitive, the next what I wanted to see was, is there some naturally arising or like a big or large orbit that you can find? Because what I really want to see is to see how when we started, I wanted to see something similar to ergodic, right? So we wanted to see how big of a mixing is happening on this variety. So I was searching for a larger orbit. So one of the good candidate is actually seemed to be the set of epimorphisms. Okay, so for that one, and it actually turns out that the action is transitive in this subset. If I look at the subsets, so I'm working in a so usually I work with free groups, but in this case we could generalize it slightly more, because I don't really need, I just want the outer automorphism group to have certain, or automorphism group to have certain properties. So suppose gamma is a finitely generated group such that the automorphisms of gamma allows us to have these elementary type of automorphisms. So the first one is it's the permutation of coordinates. So if you have an R tuple or N tuple, we should be able to permute them, and inverting the coordinate, should be able to invert a coordinate to its replace with an inverse of the coordinate, then left multiplication by a fixed coordinate and right multiplication by a fixed coordinate. So if all these, of course, free group is a special case, it has all of these type of automorphisms. So if for any gamma that includes allows these type of automorphisms, we call it a group of free type. And so for this theorem, we'll be working with groups that have gamma, finitely generated groups gamma, which has this property. Okay, suppose G is a finite group and gamma is a free group of, is a group of free type with N generators, and we want N to be large, which means at least it's greater than 2R, where R is the number of where R denotes the minimal generators for G, then out gamma is transitive on the set of epimorphisms from gamma to G. So those these are actually so we look at the set of epimorphisms, and that the action is actually transitive on this set. So the idea of this proof is basically what we do is we take all the generating vectors of G that has length N, where N is the number of generators of gamma. Okay, we call this V of Gn. Okay, and we want them to satisfy the relations of gamma too, because you're not necessarily considering them to be free. And then, if that is the case, there will be a one-to-one correspondence between the epimorphisms from gamma to G, and which I'm denoting here by epi of gamma to G, and this V of Gn. So basically, it represents all the epimorphisms. And then the idea is to prove this. What we want is basically we fix a common element from this set of generating vectors, and then we show that if you take any other generating vector of length, then we can always reduce it to this fixed element. So take a minimal generating set A1 to AR, and then we consider this element A1 to AR. And then call the rest of the elements 1. And then we can, using these elementary transformations, automorphisms that we defined earlier, we can reduce any other generating vector in VGN to this singular element, which shows that it is transitive. So no matter where you start in this set of generating vectors, you can always get back to this one point. So it is transitive on that set. So this theorem was motivated, the proof for this theorem was motivated by one of results by Gilman. I have added the reference at the end, which is on outer automorphisms of free groups, which is a paper on outer automorphisms of free groups. Okay. So this gives us a, so like I said, this gives us a out gamma, this gives us a big orbit, and in some cases, at least this is in the cases where these are actually big, if we can count the number of epimorphisms, and if they are big enough in the set, in the character variety, this gives us a good candidate to look for a large orbit. Okay. So now, once we have, if we don't have transitivity, then the next idea or next best thing for ergodicity that is comparable to ergodicity that we want to look at is something called asymptotic transitivity. So the idea is in ergodicity, so what do we mean by ergodicity? If an action is ergodic, that means it has a orbit which is dense in the whole set, right? Which means it's really, it consider almost all the point and it mixes up most of the points, right? So we want to kind of find an analogous condition to that. So the idea is, since we have finite field points, so suppose G is an algebraic group and X is a variety defined over integers. And if you look at the action of the group G on the finite field points of this variety, which we denote by X of Z mod PZ, then we say that this action is transitive if we look at the ratio of the maximum biggest orbit under this action, and then take the ratio with the size of the variety. And if this limit, when P goes to infinity, if this ratio goes to 1, then we say that that action is asymptotically transitive. Okay. 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 So now, what is some examples, like, or how, what are there is how can we get some or is it even make sense to think of a concept like asymptotic transitivity, right? So we actually have a lot of cases where we can work with cases where there is which are asymptotic transitive. So one example, or like one way, is suppose we have a group H acting on the finite field points of a variety X, and we denoting it with a subscript FQ, and Q equal to P to the power and the power of some prime P. And suppose we have a subset or a subset of XFQ, with, let's call it W, on which this action is transitive. Then what we can do is, if VI is okay, I'm going to call that, I want for this case it to be finite. If it is not finite, it's still fine, but let's just call it the index set I to be a finite for now. So if we have a finite collection of subsets, say VI, which are subsets of XFQ, such that if the order of the growth of size of this VI, so since these are all subsets of XFQ, they are dependent, and their size is dependent could be dependent on this prime Q, right? So we are interested in the case when Q goes to infinity. So in that case, if the size of VI, growth of the size of these VIs are really small, or less than, it doesn't have to be really small, at least less than the size of WFQ, then we can look at the union of this stable subset and along with this VI. And if we take union of this VI, and if we look at this union, and if the action is stable on this set, then the action will be asymptotically transitive on this subset YFQ. So if I call this union of WFQ with the union of VIs, so let's call it Y, then the action will be asymptotically transitive on this YF sub Q. So basically what it is saying is, whenever you have a stable, whenever you have a big, or not even big, whenever you have some stable subset of the variety you're looking at, you take that stable subset and then you take and union it with anything that is that has a growth that is smaller than the one that you started out with. And if their union is stable under the action, then the bigger orbit is going to be asymptotically transitive on this union space. So it's not a completely backwards, because, for example, you can think of W, F, Q, and VIs as just the orbits of the action, and the order of the W, F, Q should just be greater than growth of order of VI. Okay, so that gives us a collection of examples of asymptotic transitivity to work with. Okay, but these are like how you can cook out. So if you're given an action, how can you construct a set, or how can you construct a subset on which it is asymptotically transitive, right? But what we want is the action, looking at the action that we are interested in, and see if it is asymptotically transitive or not. Okay, so how do we look at this asymptotic transitivity? So suppose I have an action, or the action that I was already looking at, which is the action of outer automorphism group on the character variety or the home set. And so if I want to check whether the action is asymptotically transitive, what we need is to compute, to find an orbit with the size, or suppose the order of growth of the variety is q to the power k. It doesn't have to be a polynomial always, but if it is a polynomial, and suppose the order of the leading term is q to the power k, then we need to find a orbit, or the size of the biggest orbit with the same order, q to the power k, right? Then in that case, then the ratio would go to 1 when q goes to infinity. Okay, so that is one way to prove asymptotic transitivity. And one way to show that the action is not asymptotically transitive, and this is an approach that I took for a specific case of character variety. And so one approach to show that it's not asymptotic transitivity is we can stratify the variety. It could be based on, instead of looking at it as a whole, so we can stratify the space based on some condition which is more natural to look at. And then we look at the proper subgroup of this group G, where G is so we are looking at the homomorphism from gamma to G. So we look at the proper subgroups like I mentioned earlier. Then we explore like which groups of this G, like how does the mixing happen between, I'll explain a bit what I mean. How does the mixing happen between elements in different strata and between these different subgroups, and then kind of using those, try to understand if we can get some kind of, say something about whether the action is asymptotically transitive or not. So what I mean is, like, if we have this stratification, and if we know how the different elements interact within different subgroup and within different strata, then what we could do is we could use this idea, which I mentioned earlier, just call it subgroup lemma, that if we have and I'm going to work with free groups for now. So if gamma is a group on R generators, which free group on R generators, and rho is an element of home, up to conjugation even, and then rho, and if alpha is an element from out gamma, and we are looking at the action of alpha on rho, which is defined like this earlier. And if I have a subgroup of G, which is H, and there exists an alpha in out gamma, and if there is a rho in home of gamma H, such that alpha dot rho is in R product of H, then the orbit of rho is also going to be contained in HR. So this is the same idea that I mentioned in the beginning, is if you have a subgroup for G, then we take a homomorphism which is completely within that subgroup, then we always stay within the subgroup and we don't go out of the that subgroup product of the subgroup. Okay, so this is the idea. So let me look at so what I mean by looking at the case SL3FQ character varieties of F2. Okay, so F2 is the free group on two generators, and this is the fundamental group of one whole torus. My drawing is really bad, but I wanted to show what I mean by one whole torus. So it's just the torus with one hole in it, like this. So it means it has one boundary component. Okay, and I want to define something, because in this case we're not working with the regular character variety. I'm working with something called a relative character variety, and by that what we mean is, so when I'm taking gamma to be a fundamental group of some surface, then by relative character variety, what we mean is we look at the boundary component, so the corresponding component of the boundary, and then we can fix the value of that boundary component to be from specific conjugacy classes in the group G. And if we fix that, then so it's kind of like level set. So if we have a variety, and then we kind of like cut it by fixing the value of the boundary component at a fixed as a fixed point. So what I mean by that is, so we look at this homomorphism from F2 to SL3FQ, and then we take a conjugate. So G is SL3FQ in this case, and I fix a conjugacy class in G. And in this case, I only have one boundary component. It could be more than one. Then we fix each of the boundary component. So the relative representation variety is basically take the homomorphism, and then if B is the boundary component, I fix the value of B to be from this conjugacy class that I have fixed earlier. So in this case, I'm going to look at the fix the value of the boundary component to be identity matrix, and the boundary component in this case is the commutator. So AB, if if A and B is an homomorphism, it represents a homomorphism in this, because this is isomorphic to SL3FQ through the evaluation map. So if this represents an element in the homomorphism, then the boundary component, which are the images of the generators, then the commutator represents the boundary component. So I equate it to the component I, conjugacy class I identity matrix. And so this gives me the representation variety of the home set, right? Then I take the GID quotient of that relative representation variety, and it gives the relative character variety. So the idea is almost the same. I'm just looking at, but I have one more extra condition added. That's the relative character variety. So in this case, what does it mean? AB A inverse B inverse is equal to identity, means I'm looking at the commuting pairs of matrices in SL3FQ, and commuting at two pairs commute if and only if they are simultaneously triangulizable over a field extension, right? So we are working with finite fields. So, but it's not enough to just look at the if they are triangulizable over the base field. We have to go to the extension field, which make things a lot more complicated and harder to count. And like I said, in the character variety, so this takes care of, so this is the pair that we are interested in. And we want, and since it is up to conjugation, once we find one, so basically we want to find only pairs of simultaneous triangular matrices, because each of everything that is conjugate to that is in the same orbit of that, right? So we don't have to worry about each of them individually, just the representative is good enough. But for the character variety, we are looking at the closed orbit, right? So not all of these points are closed. And so the points that will finally eventually go to the character variety are the ones that are simultaneously diagonalizable. The unipotent matrices, which are the upper triangular ones, they are not closed orbits, because they have limits which are in the in the diagonal case. So these are the closed orbits of the commuting pairs, and so those are the ones that will actually eventually be there in the character varieties, So the set that we want as for the character variety is this pairs of matrices such that there exists P in SL3 FQ closure such that PAP inverse and PVP inverse are diagonal, right? So once we have this, so this is kind of the set that will give us a character variety, and each point will represent, if I look at the diagonal matrices, if A and B are both diagonal, then that is a representative of that whole orbit, conjugation orbit. Okay, so now what I want to do is we want to stratify this based on stabilizer under the conjugation action, because it's again a natural way to look at. So those matrices with the same stabilizer, I can think of them as same. So because I want to count, right? So like I said earlier, I'm trying to figure out if the action is asymptotically transitive, right? To find that, I want to get some bounds or get some count on the number of the orbits or the strata, right? So in order to count those, I want to have a idea of, I want to have some system to count the representatives, right? So we try to do it in a way that makes it easy. And the one natural way in this case is to look at the stabilizer. Okay. And okay, so the idea is, so there could be three types of cases. So the stabilizer is completely dependent on the type of where the eigenvalues of these matrices is. So suppose A is a matrix in SL3FQ that is diagonalizable to some diagonal matrix P. And if it is the case, then it is possible, the first case possibility is all the eigenvalues AB and 1 over AB are in the base field FQ. Okay, I denote this by tau sub D. I'm just writing this more G to show that I'm using it to denote the conjugation orbit and not every single pair in that orbit. So all eigenvalues, then the next case is all eigenvalues all three of them are in the extension field. So so none of the eigenvalues are in the base field, and I denote it by tau sub D bar. And then the other third case is exactly one eigenvalue is in FQ is in the base field. And so A and B is in the extension field, and 1 over AB is in the base field. Okay, so I denote it by tau bar sub D2. Actually, I wanted to put the bar on D2. Okay. So then there is a central stratum, which are the set of central elements because they are their own orbits, right? So that is the other stratum. Okay, so then so now once I have a stratification of the matrices in SL3FQ, now we look at which kind of matrices are we can pair them with. So does every element commute with each other or not? So the idea is if A is in one of these strata, then it commutes with only the same element in the same strata. It commutes with elements of the same strata within the same strata or central elements. It does not. So you cannot basically mix elements between the different strata. So this is called no mixing theorem. I wrote it in one line, but this is a really long proof, which is why I haven't stated the theorem or the proof. But so the idea is kind of look at the spaces. So we look at the spaces fixed by these matrices in each of these, and if they have different eigenvalues, they fix as different spaces, and their eigenspaces are decomposition will be different, and so we won't be able to get so they won't be commuting with each other. So anyway, so that's the idea. So this gives us some information so that this restricts the number of pairs that we can have, right? It gives us some criteria for which pairs we can have. And the counting, again, there is a the way I did is a little like I looked at each of the irreducible polynomials and then counted, because I wanted to get the count of each of the stratification. So the number of total varieties, so there are results which gives the total number of, this is called E polynomial. So the polynomial that gives the count of a variety over the FQ, it's there is E polynomial or Hodge-Deligne polynomial. So this is the E polynomial of the character variety, and there are different results that give this one, but because I wanted to get the stratification, I wanted to count the so this ended up being a longer calculation where we could count the number of orbits in each strata. Okay, so these are not all the elements, these are the orbits. So in the base field strata, we have this many elements, and this is the one with the single element in the single eigenvalue over the base fields case. So we have this many q square. So each of them has the order q to the power, first one has the order q to the power over 3, and the second one has q to the power 4 over 2, and this is the base field stratum has order q to the power 4 over 6, and the central stratum has 9 elements. So these are the counts of the stratum, right? So far we have been looking at the action. So far we have been looking at the variety itself, right? So now let's look at the action, and so based on this action, and this is an easier result. It's basically what it is saying is, if this is the orbit, that orbit of A comma B, and if it is in some strata, then like I said earlier, by the subgroup lemma, the orbit of that specific orbit of this specific orbit of this orbit, or orbit of this equivalence class has to stay within that strata, which is not clear because it is in the subgroup. But in this case, the central stratum, because most of the strata happen to be subgroups, because central strata is a subgroup, and the set of diagonal matrices over base field is a subgroup of SL3 FQ, and the set of diagonal matrices along with the extension field is a subgroup, which is not always true for all the cases because there are other elements. So it doesn't necessarily have to be a subgroup, but in case SL3 and SL2 matrices, they are actually subgroups. And that those are the all three stratum, then the complement has to stay within itself also, because each of the other stratum is a stable subset. So because of the no mixing and the subgroup lemma, the result follows that so basically it says is if you start with an element within a specific strata, you have to stay within the strata. You cannot go out of that strata to another one, stratum to the other one. So, but what did we get from that is that, so we are bounded at most by the size of the stratum, right? Because that is the biggest orbit. Any big orbit has to lay inside some strata. You cannot go out of that stratum, right? So, and if you look at the counts that we have here, none of them, so the order of the character variety is q to the power 4, and none of the other ones have q to, so this is q to the power over 3. And if I take the ratio of this with this, it will be, when q goes to infinity, the ratio will be 1 over 3, and this will be 1 over 2, this will be 1 over 6, and this will be 0 for the central stratum. So the maximum ratio that we can get, or the upper bound for the ratio of the size of the biggest orbit, that of the variety, is 1 over 2, and which is strictly less than 1. So we can never get asymptotic transitivity in this case. And so that is what I have so far. And we believe it is in true general for SL and FQ as well, even though SL and FQ has a lot more strata. So when we go to SL and character varieties, then there are, for each of the partitions of the N, we get a specific different strata, and all of them are subgroups. So we have to use some other more techniques to conclude that it is not asymptotically transitive. So that is one area that I'm working on right now, and then exploring asymptotic transitivity on relative character varieties of closed surface groups. So I am especially looking at closed surface groups of genus 2. I'm thinking, or hyperbolic surface groups. I'm thinking those could be good candidates for free groups of type, free type. And then, so we got a non-zero lower bound for the size of the largest orbit, right? But is there sorry, you got an upper bound. Is there a lower bound? Is it actually transitive within the strata? That's not exactly clear. And also looking at different boundary values for relative character variety. So the one I did right now is for the identity case, right? When the conjugacy class is identity. So I want to look at other values of for the boundary components, non-central ones. So if it is central and not identity, then the character variety is just 1 point. So it's not interesting. But for the non-central values as the bound value for the boundary component, I want to see how the action looks like. So these are the few directions that I'm trying to currently work on. Yeah, and this is the paper I mentioned earlier for the reference. And if you have want more details on any of specific, because I omitted the proof of a lot of things. So if you are interested in anything specific, like I can give more details, feel free to reach out. Thank you for listening. Any questions?